Welcome in, everyone. Today we'll be talking about lecture 14, which is DFS on graphs. We'll talk about directed graphs and we'll talk about topological sort. How are we doing on the exam? Before we get into the topics from today, how do we feel about exam one? Everyone got their grades back, had some time to hopefully digest everything and also take a look at the post I made around the exam results. So this was the distribution. We gave everyone a little bit of a boost by making it out of 35 instead of 40. And here's what we expect your predicted grade will be overall if you got this score. And this is assuming you got full score on the homeworks, the quizzes, and the participation credit, which should be doable, right? It shouldn't require you to kill yourself in order to get full score on homeworks and quizzes because there's recovery points and there's homework corrections. And there's also opportunities to ask questions on Piazza points, stuff like that. So I'm just curious, how are you feeling about the exam now that you've seen the grades? What are your reactions? How are you feeling? What's going on? Feeling bad? Okay, that's fair. And there's no right answer here. I'm not looking for anyone to say, oh, I'm feeling great after the exam or anything. I just want your raw reactions. I want to take some time and space to talk about it. And I want to make some promises about what the next exam is going to look like. Okay. People are feeling not good. People are feeling still rough. That's fair. Less terrified than before. That's good. I think a lot of people felt like there was a lot of rushing, right? A lot of time was needed in order to answer all these questions, and it didn't feel like we had enough time. Felt like it was a real challenge. Did get feedback for it. We will not have feedback. We can tell you the point breakdown if you make a private post, but for the most part, we're not going to give you like specific point, like exactly what the feedback is. You need to take a look at the rubrics for that. So the rubrics try to cover all of the ways we graded and how we actually measured all of your assignments. And you should be able to use this to get a very quick understanding of how we graded, how we were either nice on a question or maybe more strict on a question. And you can see that there's a lot of descriptions and understandings on some of the more challenging parts, right? There is a chance for improvement. We will have an opportunity to get some points back. Thank you for making it out of 35. Yeah, of course. I definitely made this exam too hard, right? Let me just go ahead and say it outright. This exam was too long for the time that we had. I know it stressed a lot of you out, especially those of you who didn't like rushing on an exam, those of you who feel a lot more stress when there's time pressure. Next exam will feel better. We're going to try to relieve a lot of that time pressure and make it so that you have a lot more time to manage across fewer questions, right? I will work hard to make sure that this, one exam doesn't define who you are as a person and, doesn't wreck your grades. And we're going to talk about that next. The next exams are not cumulative. I know that exam 2 is not going to be cumulative in the traditional sense. Like, we're going to test specifically trees and graphs on the next exam, but the actual skills you need, like figuring out the runtime for something or writing pseudocode and stuff like that, come from the first exam topics, right? Like, you still need to be able to write pseudocode. You're still going to be able to you're still going to need to find the best case, the worst case, and the average case on algorithms and stuff like that. So, you can't just forget about those topics. For the final, I was originally going to make it cumulative. I might actually change my mind. I haven't finalized and decided that. But let's go ahead and talk about grades and success for a second. I want you all to really hear it from me that grades don't define who you are. I've been in industry for 5 years, 6 years now. And many successful people who got only okay grades coming out of college, like, they're successful even though they got only okay grades, right? I know a lot of people who did really, really well in college who didn't end up being as successful. So that's one thing that I want you to keep in mind, that grades aren't the end all be all. They're not going to define who you are in 3 or 5 or 10 years, okay? At the same time, grades are not unimportant, right? Like, it's important to do your best. Obviously, some of you have scholarships riding on your GPA. Some of you are trying to make the dean's list or get president's honors. Some of you are trying to get into a good job, which requires you to have a decent GPA, right? So all of that matters a lot. That all being said, I'm going to try my best to help you. If you're having trouble with the course or if you're stressed out, please send me an email. I've been replying to emails all day, today and yesterday. If there's anything on your mind, whether it's about grades, like trying to get an A or just trying to pass the course, or trying to do something else like getting an internship or whatever else is on your mind, I'm happy to help, right? I will try my best to make as much time as possible to help you as best as I can. Now, the only thing I want to say here on top of that is that this is the distribution of grades from last semester, right? You can see that there were a lot of A's and B's coming out of this semester, and about 75% of the class got some sort of A or some sort of B, right? Almost everyone passed. And the expectation is that this semester is going to be very similar, right? So if you're feeling stressed out, know that I'm not trying to screw you over for your grade. If it turns out that the entire class needs a little bit of a boost to look like this distribution, I will make it so, just like how I curved the class, the exam a little bit this time around. And I'm really hoping that the next exam will feel less stressful, right? I'm working really hard to make sure that for the exam next week, that you feel coming in prepared, and also you feel like you're not rushing and kind of powering through and going as fast as you possibly can, okay? Was the same exam as last semester? I mean, the exam from last semester probably was not as time stressful as this exam for exam one. We're obviously going to have different exams per semester. I don't know if I answered your question though. So if you have another question apart from that, let me know. All right. So really, I just want to make sure that you all feel like you know that I have your back, that I'm going to try my best to support you in the class, and that you're not going to fail this class. All right. I'm going to try my best. If you have any questions or concerns, feel free to send me an email. All right, so today we're going to talk about DFS on graphs. We're going to go through some pseudocode, some examples, some runtime. We're going to go through properties of graphs. We're going to talk about some examples there, and then we'll go over this idea of a directed acyclic graph. From there, we're going to end on topological sort, where we'll look at some examples. We'll go through some pseudocode, and if we have time, we'll go through the runtime. In the past sections, we didn't actually go through the runtime, so we'll probably cover that next lecture. So first off, let's go ahead and do depth first search. Depth first search is very similar to the breadth first search we saw from last lecture. If you don't remember, we covered in the first graphs introduction this idea of breadth first search down here. So we want to start at some node, and we might not reach all the nodes because a graph might have disconnected components, right? There might be nodes or vertices that you can't reach from your existing current node that you start off with. And you still need to keep track of whether or not a node has been visited because we want to avoid infinite loops. And it can be recursive or iterative. We're going to look at the recursive version this time around, okay? Now, how would you actually write out the recursive pseudocode? That's like the question that we have, right? We want to be able to print out as many nodes as possible starting at some node S. And we're going to do it in a depth first manner. We're going to try to think about it in recursive form, which means we have to figure out the base case, we have to figure out the recursive case, and we have to find a way to keep track of the visits, right? We also need to combine all the elements together, but that's like, we'll talk about that once we actually look at the code, right? And then after that, once we look at the code, we'll find the runtime, we'll do some demos. So let's start right now. We're going to go and actually pull the code from homework 5. So because I wrote the pseudocode for homework 5 in anticipation that we'll cover it in class, right? So here is the recursive DFS as we defined it on homework 5. If you haven't looked at homework 5 already, please look at this video. It gives you everything you need in order to be caught up to date with the homework. It shouldn't be too long of a homework. I tried to make this homework and the next homework less stressful so that you can spend more time studying for exam 2, and also just catching up on all the other things going on in your life and in your other classes. But if you haven't already, please check out this post. But if we look and just use the pseudocode from before, what we'll see is that we have a recursive function and a helper function on top of that. Let me just pull it up here. Cool. So we take in as input an undirected graph G. It's going to take in also an S and a T. And S and T are both nodes, right? Node labels. And we're going to output true if there's a path from S to T, and then we're going to return false otherwise. Now, remember, we said originally that the goal is to print out as many nodes as possible. So what we need to do is to figure out how we're going to use this algorithm to print that out. What I'm going to do here is every time I visit a node, I'm going to go ahead and print out the node as we go. And when we actually call DFS here, what we're going to do is call DFS on the graph. We're going to call it on some node that we start off with, let's say the node 2. And then we're going to give it some ridiculous number as the second argument. Because if you think about it, DFS, based on what you saw from trees in the previous lectures, when you did depth first search on a tree, we were able to print out every single element, right? We're going to try to do the same in graph DFS. But if we're going to try to look for a specific node and return true if you can go from path node S to node T, then if we give a T that's impossible to get to, then we're going to end up printing out all of the elements anyways, right? So in order to use DFS that takes in an S and a T to print all the elements of a graph, let's set T to be an impossible node to visit, right? So let's say we had like only 10 nodes and then we said, give me the node with label 100. Well, the node with label 100 won't exist because we're going to go from 0 to 9. And so we'll be forced to go from node 2 and print out all the elements in a depth first manner and trying to look for node 100, which doesn't exist, all right? So let's go ahead and take a look at how this code actually works. If you feel good about this explanation, if you feel good about how we're going to use this to print out all the elements, just the general idea, type in DFS in chat. Give me a question mark if you need me to either repeat something or to explain it a little bit better in a different way, let's say. Okay, most people are feeling good about it. We got some question marks in chat. We'll look at some examples, which should help you out a little bit more. So the last node, this node will be impossible to get to. Yes. This node doesn't actually exist. That's what we hope, all right? So let's go ahead and take a look at how to solve this problem or how the code works for it. We're going to look at this DFS and we're going to try to explain it one step at a time about how it works. Remember, depth first search in general is path by path. You should have seen this in previous classes. You saw this on trees. We're applying this now on graphs, right? The same concept of trying to go as deep along a path as possible before we hit a dead end and then we back out and then we go to the next path as deep as possible. So in order to make that happen, what we have to do is go and actually keep track of all of the nodes that we visited so far. So in this case, if we have a visited Boolean array, it's going to have as many elements as there are nodes in the graph, right? So if I had a graph of like 10 nodes, I would have 10 Boolean elements in an array. And then we're going to call DFS helper on the graph, the starting node, the node we want to end at, and that Boolean array here. In our helper, we're going to first just set that the node we visited is true. Like the node in the visited array is set from false, we hadn't visited it before, to true, which is now we visited it, right? We're going to print out the S, and then we're going to check to see if S is equal to T, right? Basically, the recursive case is here. If we found the node we care about, we can return true right away. Otherwise, we're going to look at all the neighbors, starting from the smallest labeled neighbor, and check to see if we had visited it before. If we haven't visited the node before, the specific neighbor, then we're going to call DFS helper with S replaced with the new neighbor, as the new neighbor is the new S, right? So we'll call DFS helper on G, neighbor, T, and visited, which means that we'll make another recursive call with S now replaced by the neighbor. So we're getting closer to the end of the problem by reducing the problem by saying, oh, we no longer examine S, we now examine a neighbor, which gets us closer to the end of the path, right? T stays the same, and then visited is updated and passed along. Now, if at any point the DFS helper will return true, and we hadn't visited the neighbor before, then we're going to return true here, right? So if one of our neighbors lets us reach T, then we'll return true. If none of the neighbors return true, then we're going to go ahead and return false at the end here. All right. And we're about to walk through this code one step at a time. But one thing that I want to be very, very mindful of is this line right here, this thing, this and. All right. So we're going to talk a little bit about and. This is super important. So if you haven't taken notes about this, please take notes about it now. This and short circuits. So and short circuits its expressions. This is in Java. It's this, right? It's this double and sign. So is neighbor a node or a list of nodes? When I say neighbor, I mean a specific neighbor. So a node, a label for a node. That's a great question, right? We'll look through an example soon, and hopefully that'll give you a better intuition. But that's a great question. The other thing, back to what we were talking about, we have this concept of an and the logic here says that if, this is essentially saying if we haven't visited the neighbor before, only then will we make a recursive call. All right, so this is the same logic as what we have here by using the and. This is the same logic, right? So when we say short circuit, we mean only evaluate the left-hand side and we'll bail the and term will bail out early if the left expression is false. Okay, so only if the left-hand side is false, then we don't do the right-hand side, which is the recursive call, right? So give me a yes in chat if you've seen the concept or the idea of short circuit before, or if you've seen that term before. Give me a no if you haven't. Okay, interesting. We got some yeses in chat, a few nos. In previous classes, it was closer to 50-50. So don't think that you're alone if you typed in no. A lot of people didn't know about the properties of and in Java and in general. So again, the idea is that the left-hand side is evaluated first. We're going to check to see if the visited of neighbor is true or false, and then we're going to not it. That's what this exclamation mark does. It takes the true, turns it into a false, or takes the false and turns it into a true. And only if that entire mess turns to true do we make the recursive call. Otherwise, we skip making the recursive call altogether. Why is the recursive call in the if statement? Because we can, right? Like DFS helper will return true or false, which means we can use it in a Boolean context like an if statement, right? If DFS helper turns true or false, if it returns true or false, then we can say here, if we haven't visited this neighbor and going to this neighbor will find us a path to T, then we want to return true. Left is always evaluated before the right. Yes. In Java, that's true. And in most languages, that's true. Okay. So now that we have that all in our minds, let's go ahead and take a look at an example. If we skip the if statement and did a single return, it wouldn't work because you would then exit out of the first time you see one single neighbor. What do I want? I want this graph. No, that's not the right one. This one, yes. Someone asked in chat, if we went and just returned directly this expression, then you wouldn't be able to look at every other neighbor, right? Just think of it carefully, like this for each needs to fire for every single neighbor. If you returned this expression directly, someone in chat asked if we took this line and just returned it directly, why wouldn't that work? Because then we wouldn't be able to get to the next neighbor, right? If it returns false right away, that's no good because then we haven't called DFS on all of its neighbors. So what is the purpose of the recursive call in the code? Well, we'll see. We're about to see. It's a really good question. I'm going to try to answer it by walking through this example with you, okay? So let's go ahead and let's call depth first search on the node with 2 in it. So what we're going to do is exactly this. We're going to call DFS on G2 and 100. And you can see that there's no node labeled 100 here. So when we start with node 2, we're going to be forced to look through every single other node in the graph starting here. We're going to ignore the pseudocode in this case because I like my pseudocode better and it better gets at the point I'm trying to make. All right. Give me a 2 in chat if you're ready to start. All right. We start with DFS of 2. So I'll just write that down here. G2 and 100. And remember, the first thing we'll do is we'll make a new array of size V. We're trying to search for, someone asked, what were we searching for? We're trying to search for node 100, right? But node 100 is impossible because it doesn't exist in the node in this graph. So by giving it a ridiculous number that we'll never find, we'll actually print out every single element in the graph, right? So the first thing it says is make me a new visited array. It's going to have a bunch of falses inside of it. How many falses do we have? I'll give you 5 seconds. How many falses do I put into this graph? Go ahead and type in chat if you have it. Everyone's typing in 8. There's going to be 9 falses, right? And someone else asked, are S and T representing labels or the actual values at the graphs? It's representing labels. So these numbers inside of the circles aren't the values at those nodes. They're actually just indices into the graph itself, right? We have 9 here because if you look, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 elements, right? So we need a node for each of those elements here. And since we index from 0, it's not just going up to 8. It would be 9 because we have to include the 0 in the count as well. Okay. Wouldn't we be able to use 5? We could use 5. Yeah, we definitely could. But I chose 100 because it's ridiculous and you'll remember it, right? There's a way to modify this where you don't even need T. But for now, let's just use the algorithm that we saw in homework because then you'll feel better about how to use the algorithm for homework. Okay, so we start here. We will eventually call DFS G to 100 and visited, right? After we created the visited array. And the first thing we'll do when we look at the DFS helper, sorry, this should be DFS helper, is that we'll set the index 2 to true, right? So what we'll have here is we're going to go ahead and take a look at visited, and we'll go to index 2 and we'll set this to true now, okay? Why is the search including 7, 6, 8, and 5? Because we don't know whether or not we would reach here or not. So I think the question is, if we have a visited array, why is this so big and including all the nodes? We don't know how they're linked. Yeah, that's a good answer in chat. Someone answered. We don't know if there's like a way to get here and here. There's no guarantee. We don't know anything about the graph. So we have to assume that we might be able to visit every single node, right? Since you are solving it manually, you can see visually that you can't get to 5 or you can't get to 7. But if from a program's point of view, you definitely can't know for sure, right? It's a good question. All right, so we know that we'll set this to visited and then we'll print it out. So we're going to print out, I'm just going to write it here. We print out 2 first, right? And then we're going to look at all of its neighbors. So we say for each neighbor of 2, starting at the smallest labeled neighbor, we're going to check to see if that neighbor has been visited before. That's what this line means. This part of the line means. And if it hasn't been visited before, then we'll go and make a recursive call on that neighbor and see if he'll return true. Okay. So in this case, what's the first neighbor? Well, if we look, 2 has 2 neighbors. We have 1 and 3, right? In which case, we're going to go ahead and call DFS helper on G1 100 and visited, right? 1 comes from the fact that we passed in neighbor as the new S here. So the second argument will always be the S. In this case, S will be 1. We're still looking for a 100 because we still need that ridiculous number so that we're forced to look through every single element as much as we can in the graph. And we picked 1 over 3 because 1 is the smaller of the 2 labeled nodes. All right. So if we go and play through this animation, we'll see that we look at 1. We'll mark it as visited, right? So we're going to go ahead and look at index 1. We'll set that to true. And then we're going to go and print it out into onto the screen, right? We'll print out S, so 1 gets printed. And then we'll check to see if S is equal to T, right? We already said earlier that there's no way that you could print out, find 100 and 1 is not equal to 100, right? So we keep going. And then we look at all of its neighbors. All right, I'll give you 10 seconds. What's the next node that we call for DFS helper? What's the next call look like here? If we are following along the code and you feel good about where we are right now, what's the next node that we're going to visit? Go ahead and type in chat. What do you think? Okay, people are typing in 0. That's great because that's true. So if you're confused, always feel free to type in question mark. I'm happy to explain it in more detail. I know that some of you were confused about how the recursion works, but I'm trying to explain it through this example. You can see here that if the node hadn't been visited before, so 0, at index 0, this is going to be false. The exclamation mark will make it true. So this hasn't been visited before, so we return true here. And then that means we're forced to make a recursive call to DFS helper of G0 100 and visited, right? So we're here. So if we keep hitting next, you'll see that we reach out to node 0 here. And this node will mark it as visited now. We'll print it out. And then we'll look at its neighbors. So here's a question, 10 seconds. Does 0 have any neighbors to look at? Yes or no? Will we go into the for loop is really what I'm asking. Will 0 go into this for loop? Yes or no? I'll give you another 5 seconds. Okay, we got some question marks and then a fair bit of no's and yeses. A lot of people are saying no. But here's the thing. This for loop says go through every single neighbor of S, starting from the smallest labeled neighbor. That means we will actually try to look at the 1. There's nothing telling us we wouldn't. We will go into the for loop. The answer is yes, we will look at the for loop. Whether or not we'll make a recursive call is a separate question. We didn't make a recursive call for 1 again, but we did go into the for loop and we did try to look at 1. But since 1 has been visited before, when we look into the array, index 1 will be true. When we have the exclamation mark here, it turns the true into a false, which means that this left-hand side is false, which means we never go into the recursive call. All right. Type in 1 in chat if you feel good about this, question mark if you need a refresher or a different explanation. So we do go in to the for loop. And we do look at the neighbor of 0, which is 1. And so every time we look in the for loop, we're going to check to see if we have visited that node before, if we visited that neighbor before. We have visited 1 before, which is why we don't make another recursive call. This is why we're going to get O of V plus E. Yeah, this is why we'll get O of V plus E. By the way, I know some of you prefer looking at the slides as we're going through, so I'm going to go ahead and post in chat if you want the slides. We don't do the recursion, but we still enter the for loop. That's a great way to put it. That's exactly correct. Someone mentioned that in chat, right? So once we look at all the neighbors of 0, which was only the node with 1 in it, we're going to go ahead and return false here. So this thing here, this entire thing gets crossed out because we're done with it and we return false. Okay. That means we'll go and go back to the world where we called DFS on 1, because that's why we called DFS on 0, because we were in the middle of trying to figure out DFS on 1. This still counts towards the runtime, right? Even though checking the visited is constant work. Yeah, we'll check all of the edges and we'll explain that in a bit. It might help for visualization if I nest the class. You mean nest the calls here like this? Okay, cool. So I will do that. There we go. So we called DFS on 2, which called DFS on 1. DFS on 1 called DFS on 0. And DFS on 0 returned because it tried to look at 1, but 1 had already been visited. From there, we're going to go back to the world where we were calling DFS on 1, right? Because we were in the middle of looking at DFS on 1 when we called DFS of 0. Here's the next question. I'll give you 5 seconds. Don't type it in chat yet. What is the next node we look at from 1? We're here right now. If I hit next on the animation, what's the next node that will have a little animation toward it? Okay, go ahead and type in chat. Okay, we got some people typing in 2 and a lot of people typing in 3. It's going to be 2, right? Because I just said it doesn't matter if we visited it or not. We're always going to look at every single neighbor. 2 is the next smallest neighbor from 1. So we have to look at 2 next. Even though it's been visited, which means we don't make a recursive call, we still look at the 2, right? So again, we first examine the 0 from 1. We look at the 0. 0 tries to look at 1 back, but it doesn't work because it's been visited before. So we go back to 1. 1 will now look at 2. 2 doesn't work out either because it's already been visited. So then we go back to 1 and we then try to make a call to 3. 3 hasn't been visited before, so this will return true, which means we'll actually call DFS helper on G3 100 and visited, right? You can see here that it's on the same level as calling DFS helper on 0 because we're looking at the neighbors of 1. And so 3 is also a neighbor of 1. We're going to go ahead and walk through it. It's going to mark 3 as visited. So I'll just go ahead and update that. And then we're going to print 3 out. And then we'll look at all of its neighbors, right? Now, if you've fallen for my trap in my previous question, hopefully you won't fall for it now. I'll give you another 5 seconds. What's the next node we try to examine in the for loop? Okay, everyone's typing in 1. Good job. It is 1, right? Because even though 1's been visited before, we're still going to look at 1 because that's what the code tells us to do. We look at 1. We realize it's visited, so we don't make another recursive call. And then we look at the next node that is a neighbor of 3. I'll give you another 5 seconds. Which one happens next? Okay, everyone's typing in 2. Very good. We do try to look at 2 now. 2's been visited before, so we bail out of that. And now we look at the last neighbor, which is 4, right? So we'll call DFS, in this case, DFS helper. Since we haven't visited 4 before, we can call DFS helper on G4 100 and visited. We're going to go ahead and just like before, we're going to go ahead and set 4 to true. We're going to print 4 out. And then we're going to look at all of its neighbors, which it has no neighbor. Oh, sorry, I lied. I almost made a mistake. It does have a neighbor. It has 3, right? We try to look at 3. It's been visited before, so we don't do anything. We don't make another recursive call, but we do look to see if it has been visited before, which is a constant time operation, like someone mentioned. And then now we're done with the value. So we can go ahead and cross this out and return false here, right? Because again, every time we visit, if we couldn't find the T that we were looking for at the current node, even if we look through all of the neighbors, we'll return false. So type F in chat for number 4. Cool. If you feel good about this, you should be typing F. If you're confused, you should be asking a question or otherwise typing in a question mark, right? We go and we visited F. F is good. Sorry, we visited 4. 4 is good. We go back to the world where we were processing 3. 3 now has processed all of its neighbors. It has not found any neighbor that will find T. Do graph nodes generally have an overall index? Yes. Usually when we're solving problems and writing algorithms on them, they have labels. We covered the idea of labels in the previous slides in lecture 13. But generally, every single graph will have unique labels for each node, usually indexed from either 1 or 0. Okay, we do that. Well, we're done here, right? That means we've processed all the neighbors of 1. All of the neighbors of 1 are done, which means that we couldn't find any of them that would take us to T. Of course not, because we tried to get to 100 and there's only 9 nodes in the graph. And so we return F from 1 as well. Why would it return false? Because we have this line on the very bottom of the code that says if we cannot look through, if we look through all of the neighbors and we call DFS helper on all the neighbors, or we try to see if they've been visited before, and all of them return false here, then we will never return true inside of the for loop in the if statement. And so therefore we should return false. Remember, the question is there a path from S to T? S is going to be some node that we're currently at. And the only way we can get to T is if we go and call DFS helper on all of our neighbors. And if none of them return true, that means that I can't get to T from where I'm at right now. So I should return false, right? It's a good question. This should always return false unless there are 101 nodes in the graph. That's a good way to put it, right? Because right now we will never have a node labeled 100, which is why we're forced to print out every element in the graph from starting at S to every other reachable node. Okay, so at this point, we're back at DFS helper of 2. What's the next step? I'll give you 10 seconds. Are we done or is there a next step? What is there left to do, if anything? Go ahead and type in chat if you have it. Someone has it. Okay, someone said return false. Someone said no more. Someone said question mark. A lot of question marks. Remember, we were in the middle of looking at 2's neighbors. We just finished looking at the neighbor DFS of 1. You can see from the red line here. The next step is to look at the next neighbor, which is 3. We look at 3. Oops, we go back here and we look at 3 and say, hey, can we go to 3? Should we look at 3? Has 3 been visited from 2? And we have visited 3 in the past, so we can't make a recursive call here. So we have to do that before we're finally done here, and then we're done with the overall expression, and we return false here, right? Because we added a print statement, inside of DFS helper, we were able to print out all the elements here. And because we are methodical and working exactly how Java would do, we looked at every single element and every single edge. We actually looked at every single edge twice in this algorithm because we wanted to look from 2 to 1 and then also 1 to 2. All right. If you feel good about this, or if you're at least ready to move on, let's go ahead and try to find the time and space complexity based on what we see here. If you have questions, you feel free to ask, but I'll give you 90 seconds to try to answer the 4 questions we normally ask. What's the best case? What's the worst case? What's the space complexity? And what's the average case? So at node 4, we ran out of neighbors to look at, which is why it returns false. At every node, whenever we run out of neighbors, we return false. 4 tried to look at 3. 3 already was visited before. So then after 4 ran out of neighbors to look at, which was only the node 3, we return false. What is in V plus E question mark? Oh, that's a great point. One thing that I didn't expressly define, which we should do here, is these 2 terms. Like we said in last lecture, E with 2 lines around it is the number of nodes in the graph. And then E with 2 lines around it is the number of edges in the graph. All right. And we want to put our best case, our worst case, and the average case in terms of these 2 variables. All right. N can be put in terms of V and E, but typically for graph algorithms, we actually just use these directly, and we'll do so going forward. All right, so I'm going to make some space here so that we can play around with this and think about it carefully. Do we not do visited to 5? Yeah, because there's no way to get to 5. You can see here that there was no way that we could get to 5. There was no edge to reach to 5. And as a result, 5, 6, 7, and 8 were never visited. All right, there's about 10 of you who haven't voted. Please do so now. Let's go ahead and try to get to 100%. That would be awesome. I don't think that's happened exactly once in class. We got pretty close. So in code, we hold all the neighbors in a list like a tree. Yeah, that's exactly right. I mean, you saw from last lecture, we had adjacency lists and adjacency matrices. So that's kind of how we normally represent graphs. One thing that I didn't mention, which we should mention here, is that we're assuming that getting all the neighbors of S will take constant time, right? So let me go ahead and type this up. At the top here in big bold text, and you should write this down, assuming getting a list of neighbors takes O of 1 time, then the best case, well, the best case doesn't matter because it's going to take O of 1 time, all right? I'll give you about 10 seconds or 20 seconds. What scenarios will we enter the best case? What graphs do we pass in, regardless of their size, will take O of 1 time? When we look at the poll here, a lot of you thought it was O of 1, but it was almost an even split between O of 1, log of n, and O of n. So if we added up all the people who voted log of n with all the people who voted O of n, we end up with the same number of people who voted O of 1. Go ahead and type it in chat. What do you think? All right, we got a bunch of different good answers. There are 2 scenarios that we can think about, right? The first scenario is no matter how big your graph is, if S is equal to T right away, then we return right away, right? So in other words, if I have a million nodes in a graph and I'm looking for S is equal to, if I start at S is equal to 42 and then T is also equal to 42, then we're going to hit the base case. We're going to bail right away, right? It doesn't matter how big my graph is. If I set the starting point to be my ending point, I'm already done. The other one, which I think people are really cool for thinking of, and I was surprised, I wouldn't say surprised, actually. You all are outstanding bunch. So you came up with this, which I wasn't thinking of originally. Any graph with no edges would also be a problem here, right? So if I had a graph with a million nodes, but no edges between any of the nodes, then we're going to look at all of its neighbors. We don't have any neighbors and we exit right away, right? So it doesn't matter if we start at node 10 or node 1,000,000. If the neighbors are all empty, if we don't have any neighbors to any of the other nodes, we're going to end up in an O1 scenario, right? We exit right away. Now, the worst case, though, is going to be something like O of n, right? O of n, or in other words, O of v plus e. And a lot of you said that the worst case is exactly that. About half of you, it looks like. The reason why we know this is the case is given a fully connected graph, we will look at every single node exactly once and every single edge exactly twice. Right? We know this to be true by looking at the example code that we did, or the example that we went through for the code, right? We'll iterate through, we'll make a DFS helper call to every single node we can reach. And if the nodes are fully connected, if the graph is fully connected, then that's every single node. And then we do this for loop, which says, look at all of my neighbors, which means that whenever we go through, we're going to look one direction from 2 to 1, and then another direction from 1 to 2. Likewise, we looked from 1 to 0, and then 0 to 1, we looked at 4 to 3, as well as 3 to 4, right? So we know that if we look at every single node exactly once, that's an order of V with 2 lines around it. And if we look at every single edge exactly twice, then on order of, like, it's going to be O of, E here with 2 lines around it. Because we don't care. 2E is the same as O of E, right? So this is the answer to our last homework question, right? Yeah, that's exactly right. Good call. I am giving you the answer to this. I am using this so that you can maybe answer this one on your own. But the whole goal is to make this homework super chill. I'm not here to trick you. There's no gotchas. This homework's supposed to be really straightforward, okay? So in this algorithm, under what case will it return true? Well, if we try to find a node that is actually in the graph, like for example, if we try to go from 2 and try to find 1, then the first call we'll make to DFS helper will return true right away. I'm confused on how looking at all the neighbors will be O of 1. No, looking at all the neighbors will not take O of 1, but getting a list of the neighbors, we're assuming takes O of 1, right? Don't get that confused. That's a really good point. Looking at all the neighbors is going to take time. Right? It's going to take this much time. But getting a list of neighbors, just getting the list without looking at all the elements inside will take O of 1. That's the assumption we're making. All right. That was a good question. Does that help? So someone asked hey, how is it that we're getting O of 1 when we're looking through all the neighbors? But the answer is it's not O of 1. But getting the list before we look at it, just getting me a list, we're assuming that takes O of 1 time. What does it mean by getting a list of neighbors? Well, when we say for each neighbor of S, starting at the smallest labeled neighbor, we have to basically have a for loop that traverses through every single neighbor, right? In other words, if you had an actual code, we would have something like g.getNeighbors of some S. And I'm saying that this function call should take O of 1 time. Just because it's based on object-based lookup or a pointer lookup? Yeah, because we're going to probably actually in a real life scenario represent graphs as a hash map of hash maps instead of an adjacency list or an adjacency matrix, which would take O of 1 time to grab. All right, good questions. All right, so let's go ahead and take a look at the average case. The average case is going to be O of V plus E looks something like the worst case, which is the hand wavy explanation. right? I'm not going to force you to like think about this too hard, but let's just imagine that in the average case, we're going to have some sort of graph. We're going to visit most of the graph, which is going to be mostly linear, right? So we don't even say O of n for average. Yeah, because we want to put things in terms of V and E. We could have said that O of n is true if n is equal to V plus E, right? We do want to say it's linear with respect to the number of nodes in the graph and the number of edges in the graph. You can say it's linear, which is another way of expressing O of n. But in this case, if we want to be very specific, very methodical about how we're doing the accounting, we visit every single node exactly once. We visit all of the edges exactly twice per edge. And as a result, then the sum of those two things is how much our runtime is, right? We already described in the best case that we could come up with a graph with a bunch of nodes but no edges, which is why the factor of E needs to be independently written. Okay, let's do space complexity now. Space complexity, a lot of you said it was O of n. So that's exactly what I'm thinking too. You can just imagine a graph that looks very much like a straight line, because for all of the calls to DFS helper, like each of those calls to DFS helper is a call we have to remember if it hasn't returned yet. So in this case, if we started here and we ended here, right? We started at the top, we ended at the bottom. We're going to call DFS helper on each of these nodes, and none of the nodes return until we get to the very bottom, right? If you don't understand this argument, go ahead and watch the video again from like this lecture, because we talked about it here, where every single node, did I talk about it here? Sorry, I did not talk about it here. I talked about it here in binary trees, where every time we have a function call, we have to remember that we are in the middle of a function call if it hasn't returned yet, right? So that takes space in itself. So if we end up in a scenario where we look like this, we're going to remember all the calls to DFS helper. And we have to remember them until we hit the very last node in our graph, right? Let me just be absolutely clear. These are bidirectional, or that you can just use lines here. But there's going to be as many recursive calls as there are nodes in this case. We make a recursive call for each node if the nodes are lined up in a list-like structure. We'll have to remember the recursive calls. Why is it V plus E instead of V times E? Well, because we don't look at every single node when we're looking at every single neighbor, right? Or in other words, the edges are only added together because we visit every edge exactly twice. If we wanted to multiply V and E, we would have to look at every single edge like dozens of times, right? If we have this graph, then we would have to look at it like 8 times per edge. Best case space would be O of 1. Yeah, this is just talking about the worst case space complexity. Okay. Any other questions before we move on? Why does it say that there are no edges? Wait, hold on. Why does it say that there are no edges not breaking null for runtime not being dependent on the input size? That's a great question. Okay, so the question here is, if we say in the best case that there's a graph with no edges, I can make a graph that's 1,000,000 big because I have 1,000,000 nodes. I could have 1,000,000,000 nodes. I could have 1,000,000,000,000 nodes. I'm just saying that the edges are 0, right? If you don't buy that, if you feel like fixing the size of a certain part of the graph is still cheating, then go with this definition, which would also still be true, irregardless of whether or not you fix the size of the number of edges. Why is it that the best case space O of 1? Wait, is the best case space O of 1? Let me think about that. The best case space is O of 1 because if we had a graph with no edges, then we would end up just making a recursive call and then stopping, right? Regardless of how big the graph ends up being, or that we say that S is equal to T and we'll return right away, which means that we don't use that much space to return right away, even if the graph is huge. Edges do cost space, by the way. Someone pointed that out in chat. Edges do cost space, so that's something to keep in mind. Even if there's edges for the graph, if the node we start at has no edges, it would still be O of 1. Yes, if you just have one single node like this 5, we start at 5 and we're looking for, let's say, 2. Then if we started and called DFS on graph 5 and 2, then this would still return right away. We're still creating an array of size V. Oh, yeah, you're right. You are correct. Yes. Yeah. Okay, so the best case actually will still be, yeah, sorry. Let's make that clear. Best case space complexity is O of V, because even in the worst case, or sorry, even in the best case, we have to create visited, which takes O, which has V elements. All right, good call out. I didn't mean to make that mistake, but I'm glad you caught it. We hadn't covered best case space complexity in the previous classes, but this is a really good point where even in the best case, we actually still need to create an array of size V, which means that we still have O of V to be used. Yeah, we always create an array before calling the recursive call. So those of you who are saying that even in the best case, it should be O of V, it should be, you are correct. So this doesn't actually print out all of the nodes, as in like every single node in the graph. How would we do that? We would wrap this in a for loop. We would say that for all unvisited. So the question is, how do we print out every single node in the graph? For all unvisited nodes in G, then call DFS on that node. For each, so let's say for each unvisited node in G, then call DFS here. And what we would have to do is we would have to make visited a global. So we would maybe say here, if we want to print out every single element, we would say visited is equal to this array of size V. And then we could go ahead and like just call DFS helper on G, the node, let's say some ridiculous number. So V itself and then visited. And then that's how we would print out every single element. Can you fix the best case space complexity by checking if S is equal to T in the initial array? Or would that be inefficient coding? I mean, we could. There's always ways to make things slightly better. But in this case, we don't mind it too much. Usually we don't worry about it, trying to optimize in that way. It wouldn't be inefficient coding. If it comes up a lot in real life, then of course you would want to create a one-off if statement for it. But assuming that we're thinking in terms of theory and not real life, then we usually don't worry about it in a theoretical point of view. Yeah. Okay. So I'm going to leave this here. We're going to go ahead and take a 5-minute break. And we'll come back at 6:30, and then we'll look at graph properties. Right. I'll leave this up here in case people have questions. And we're just chilling right now. Is it possible to optimize this algorithm further by eliminating T from it? Yeah, if we actually just wanted to print out all the elements in the graph, then we could change this so that it looked differently. I'm not going to do that here because I want to show you the search, the actual like looking for a certain node value. And someone just started vacuuming outside. I can't tell. Can people hear the vacuum outside? We're on break, by the way. People can hear a loud noise that just came up. Okay, I have to mute myself. Hopefully it'll go away. All right. I have someone outside of my apartment doing a vacuum, so I've turned the gain down a little bit on my microphone. Can people still hear me okay? And can people hear the microphone? Can people hear the vacuum? It's okay? All right. Okay. So let's go ahead and move forward. I wonder if anyone does cappuccino art, by the way. If anyone does latte art. I've seen latte art up close and it's always really beautiful. If y'all are doing it, it definitely takes a lot of skill and care in order to get it looking really good. Anyways, we're gonna go ahead and talk now about properties of graphs. Properties of graphs, there's a lot of different properties, but there are a few that we care about right now. So there are two pairs of properties, I would say. There's this idea of directed and undirected, which are pairs of each other. So undirected means that the edges of the graph don't have arrows, like one directional arrows. And then directed means that the edges of the graph have arrows indicating the direction, right? So an example in real life is, for example, if you have friends on Facebook, if I'm friends with you, then you're friends with me. Or if I'm siblings with my brother, he's my sibling as well, right? There's no getting out of that, right? We're stuck. A directed graph is different because we can follow each other on Instagram or Twitter or whatever, but we don't have to. I can follow you and you don't have to follow me back. I can follow Beyonce, but she's probably not going to follow me back, right? And so the idea here is that directed and undirected graphs represent different real life scenarios that we definitely see come up pretty often, okay? So the other pair is cyclic and acyclic. So cyclic means there's at least one loop, which is a path that leads away from a node that returns back to the node without using any of the same edges. So for example, I could go ahead and write a graph here. Someone's saying start a GoFundMe to have Beyonce follow me back. I don't need that sort of notoriety. Please don't. I don't even know how GoFundMe would work. Like, it's not like we could pay Beyonce to follow me. I think I just need to be cool enough for Beyonce to want to follow me, but I'm not that cool. I got two things going for me. I know how to code and I reasonably know how to teach how to code. And that's all I got. And I don't think that is above Beyonce's notice right now, right? All right, so let's take a look. Here's an undirected graph. You can tell because there are no arrows on these lines. And you could say that this is cyclic because you can go from this node to this node to this node, and then this node to this node, right? Another example of a cyclic graph, if you're looking at a directed graph, here's a directed graph. Here's an arrow, right? So I'm following this person. They can follow me back. If I'm going in a loop here, I can go one edge, second edge. There are two distinct edges here, so this counts as a cycle. If I had an undirected graph here, and I just drew one line between them, is this a cyclic graph or an acyclic graph? If I just had an undirected graph and there's one line between two nodes, does this count as a loop? Go ahead and type in chat if you have it, or question mark if you're not sure what I'm asking. Okay, a lot of people, well, actually, I'll give you some time to type it all out. Okay, some people are confused. A lot of people are confused. So we're saying, is there a loop in this graph? Right? Is this cyclic, which means that there exists a loop, or acyclic? So the answer for this one on the top here should be no, because this is an undirected graph. I have to go from A to B, but I can't use the same edge to go from B to A. That's the rule here. If I go down here and I say this graph here, this graph checks out because I can go from A to B, and then I can use a different edge to go from B to A. This graph also checks out because I can go from A to B, B to C, and then C to A, all using different edges. So like the key here is to realize that you can't reuse the same edge twice in order to draw a loop, okay? An acyclic means no loops exist. So for example, this is an example of an acyclic graph. If I remove some edges here, that would also be acyclic, right? Okay, so let's look at this example. Let's take about 10 seconds to think. Is this directed or undirected? And is this cyclic and acyclic? Right? Does it count for an edge that's reflexive? So if you're talking about in a directed case, if you have an edge going out and an edge going in between two nodes, then that counts as a cycle. All right, we're just going by that definition. Oh, you can't. Yeah, no. This, someone's asking, can this happen? This won't happen. This is called a multigraph, and we're not covering multigraphs in this class. There's another couple of terms for this. I'm going to call it a multigraph. You can look it up on Wikipedia. People don't agree on what to call a node that points to itself, but in our class, let's just imagine that can never happen. All right, so is this a directed graph, an undirected graph, a cyclic, or an acyclic graph? So we know this is undirected because there's no arrows on any of the lines. So this is undirected. And we know it's cyclic because we can go from 1 to 0, 0 to 2, and then 2 to 1. Likewise, we can go from 1 to 2, 2 to 4, and then 4 to 3, 3 to 1, right? So this is cyclic because there's ways to go around here, right? Let's go and identify all the cycles. I identified one. I said 0 to 2 to 1. I can also say 1 to 2 to 4 to 3. Is there another one? I'll give you 10 seconds. What's the last cycle here? It says identify any cycles. We have more left. Go ahead and type in chat if you have it. We want to go and say, okay, we can go from 0 to 2 to 4 to 3 to 1 all the way back to 0. Right? So we go the long way around as well. So we have this one here, we have this one here, and then we have this one here. Cool. So an acyclic graph would be basically a tree. Yes, very good. I didn't bring this up. I was going to bring this up in another lecture, but all trees are acyclic graphs. Not all acyclic graphs are trees, though. Right? So, for example, we could have a tree. A tree here. Here's an acyclic graph, right? This is a tree. It's also an acyclic graph. But we can have this be an acyclic graph, but it's not a tree. Right? Here's an example of an acyclic graph. That is not a tree. So you're not going to count order to matter here. Yeah, the ordering doesn't matter because it's a loop, right? You go in a circle. You don't necessarily care about where you begin and end since it goes all the way around. All right, so the last question we have is how do we represent this as an adjacency matrix and how do we represent this as an adjacency list? I'll give you about 1 minute to think about this on your own and to try to write this up. An adjacency matrix, if you remember, looks like a bunch of arrays of arrays. So there's going to be a bunch of elements in here, right? And you're going to have to figure out what this looks like. In fact, this is exactly what we're doing in homework, which is why I'm spending so much time doing it in lecture. The hope is that you can take what you've learned in lecture and apply it to the homework in a way that's relatively straightforward. So I'll give you about 1 minute to do both the adjacency matrix and then the adjacency list, and then we'll go through it together. All right. So you might not have finished, but go ahead and hit enter. What do you have so far? We'll go ahead and take a look at this together. So don't worry if you're not 100% ready, and don't like just copy and paste someone else's graph. There's no point in that. Just tell me if you're not ready or if you didn't finish, right? That's totally okay. Okay, nice. We're going to go through this together. So don't worry if you didn't get through everything. That's totally okay. Let's start with the very, very first one, right? We're going to go ahead and take a look. We know that for the matrix, we have to start with all of the neighbors here of 0 will have a 1 in the corresponding index. So if we look at the very first row, we know that 0, 1, 2 will have an edge, right? Like this is saying there's an edge between 0 and 2, row 0, index 2. And then there's also an edge between 0 and 1. Okay? If we keep going, I'll give you about 10 seconds to think about this. If we follow the same pattern, for 1, what should this graph look like? Or what does this row look like? There's 8 elements here, so hopefully you can type it in here. I would go row by row every time just so that it's easier to understand. And then we'll go through it together from here, right? I'll give you another 10 seconds. What would this next row that I'm highlighting right now look like? Go ahead and punch it in if you have it. So we know that 1 has an edge to 0. 1 has no edge to itself. 1 has an edge to 2. 1 has an edge to 3. And 1 doesn't have an edge to 4, 5, or 6, so they all stay 0, right? If we keep going, the same pattern occurs. So there's an edge between 2 and 0. There's an edge between 1 and 0. There's no edge between 2 and itself. There's no edge between 2 and 3. There's an edge between 2 and 4. And no edge between 2 and 5. And no edge between 2 and 6. There's an edge between 3 and 1. There's an edge between 3 and 4. And no other edges. For 4, there's an edge between itself and 2. There's an edge between itself and 3. There's an edge between itself and 5. And then no edge between itself and 6. 5 has an edge to 4. 5 has an edge to 6. And then 6 has an edge to 5. Okay? So this wasn't meant to be too scary. It might have taken you a little bit more time, and that's okay. The goal here is to make sure we can represent this graph pretty accurately. So let's go ahead and try to do the same for the list, right? Let's go ahead and think about what goes in the first row. I'll give you 15 seconds. We know that 0 has a list of neighbors here that we have to fill in. It shouldn't be too scary, so I'll give you another 5 seconds here. And then after 5 seconds, go ahead and hit enter for me. Right, so we should have a neighbor for 1. We have a neighbor in 2 because 0 goes to 1 and 0 goes to 2, right? Likewise, we'll have 1 go to 0, go to 2, go to 3. 2 will go to 0, 1, and 4. 3 will go to 1 and 4. 4 will go to 2, 3, and 5. 5 will go to 4 and 6. And then 6 will go to 5 here. All right? So this is what it looks like for an undirected graph that has cycles to be represented as an adjacency matrix and an adjacency list. This won't go away, right? We will ask questions on how long it takes, for example, to get a certain element out of an adjacency matrix or get a certain element out of an adjacency list. That will be something we care about in a bit. All right, so let's look at example 2. So for example 2, is this a directed or undirected graph? And is this a cyclic or acyclic graph? I'll give you 10 seconds and then afterwards I'll say so and we'll all hit enter. Is it possible to determine if a graph has cycles using an adjacency matrix or an adjacency list? It is certainly possible, but you basically need to write an algorithm on how to take an adjacency matrix and determine whether or not there's a cycle in it. It's not like super easy. There's not like a one size, like a very quick way to figure it out. Although you can answer certain questions around, for example, whether or not something is a source or a sink if you use an adjacency matrix or an adjacency list a lot. And you can do that relatively quickly. All right, so is this undirected, directed, cyclic, acyclic? Go ahead and punch in chat. So we know this is directed because there are arrows, and we know this is cyclic because there's still a direction that we can go from 1 to 0 0 to 2, and then 2 to 1, right? So this is definitely something that has a cycle. We no longer have a cycle up here because we can't go from 1 to 2 or 1 to 3, and we can't go overall through this entire cycle because we can't go from 2 to 4, right? So there's only exactly one cycle here now. And if we wanted to look at the adjacency matrix and the adjacency list, now we have to go and try to figure out how to modify these in order to get the right answer. So I'll give you another minute, and I'll even paste my solutions here from the previous example and see if you can go ahead and change those so that it looks correct relative to what we have now. So what I'm saying is that these two that I pasted into chat are not correct because now we have a directed graph instead of an undirected graph. So we're going to have to look at how to change the matrix and change the list so that it has the right things. Okay, go ahead and paste it in if you have it. What are the ones we want to do here? Right, hopefully you had a little bit more time to play around with this. The goal is for you to feel good about how this actually looks. We're getting a lot of good answers here, and then we'll go through it together very soon. Nice, the vacuum finally went away on my side. All right, so let's go ahead and take a look at the list first because it's easy, right? So the list here, instead of just having a neighbor to 1 and a neighbor to 2, we only have a neighbor to 2, so we take out the 1, right? If we look at 1, it only has a neighbor to 0 and nothing else, so we take out the 2 and the 3. For 2, it only has a neighbor to 1, so we take out everything else besides that. And for 3, we only have a neighbor to 1. For 4, we only have a neighbor to 2 and 3. And then 5 only has a neighbor to 5 and 6. And then 6 doesn't have a neighbor to anyone, right? So hopefully this looks familiar or makes sense from your point of view on what the adjacency list will look like. The matrix will be very much the same changes. We want to point to 2, but not 1, so we put a 0 here. We want to point to 0, but not anything else, so we put a bunch of zeros here. Can the exam be fully comprised of matrix and list questions? I mean, no. The short answer is no. I was going to give a snarky answer, but I figured giving a more honest, straightforward, can't be construed as anything else answer will probably be best. All right, so 2 will only point to 1. It won't point to anything else. 3 will point to just 1 and nothing else. 4 will point to 2 and 3, but nothing else. 5 will point to 4 and 6 still, and then 6 won't point to anything. All right, cool. All right, so let's do one last one, and then we'll take another break. So you see example 2 and 3. The only differences are these two arrows got moved, right? So if this is the case, this is still a directed graph, right? Because we still have arrows. Is this cyclic anymore? Yes or no? What do you think? Take a look at this graph, take 5 seconds, and then type in whether or not you think this is cyclic. Yes or no? Yes, this is cyclic. No, it's not cyclic. Go ahead and type now if you have it. Okay, we're getting a bunch of different no's in chat, which is great. And so let's go ahead and take a look here. All right. We know that the only place that we could have a loop previously is this spot here. We tried to go from 0 to 1, 1 to 2, and then 2 to 1. That's no longer the case. We no longer can have a cycle here, right? And then when we do this part here, we still have the same problem. There's no way to go and complete the cycle, and there's no way to go and complete the cycle here. So this is acyclic. I just unplugged my headphones. So quick check. Can everyone still hear me okay? Give me a yes in chat if you can hear me fine. All right, thank you. Cool. So is there a way to derive cyclic from the matrix or the list, or do we have to draw it out? You basically have to draw it out. That's the most reliable way. All right, so we know that this is directed still. We know this is acyclic, and we know that we have to change values here in the list and in the graph. So let's do the matrix first, right? So in this case, we have 1 pointing to 2 now. So instead of it points to 0, it also points to 2. And then 2 no longer points to anything, so there's a 0 here. 3 can point to 4, so 0, 1, 2, 3, 4. But 4 does not point to 3 anymore, so this gets zeroed out. Likewise, on this side, we have 3 pointing to 4, so there's a 4 here. And then 4 does not point to 3. And then we have 1 pointing to 2. And then 2 doesn't point to anything here, right? So 2 is the judge. In this case, not everything points to 2, so therefore it cannot be the judge. But you do bring up a good point that you're trying to look for nodes that don't have any arrows pointing out when we are trying to figure out that problem. The matrix will be a diagonal mirror if it's not directed. Yeah, so basically it'll look something like this, but that's not a guarantee to decide whether or not it's directed or undirected. It could just be that every single node has another edge pointing at it, right? Like if we had a directed graph that looks like this, it would still be directed, but it would look a lot like an undirected graph in the matrix, right? So the question was, hey, how do we determine from the matrix alone whether or not something's directed and undirected? You can't always tell. There's a world where we could make this look kind of bad, right? If it's asymmetric across the diagonal, then you know it's directed. But if it's symmetric, it's not guaranteed that it's directed or not, okay? So let's do a directed acyclic graphs real quick, and then we'll take a break. Actually, let's take a break first, and then we'll talk acyclic directed acyclic graphs. And we're going to take like a 2-minute break here because there's some announcements I need to make, and then there's also a lot more material we have to cover here. So we'll come back at 6:55, and then we'll go through some announcements, and then we'll look at directed acyclic graphs. All of you are asking really good questions. I'm really happy you're all engaged, but this means that our breaks have to be slightly shorter because I need to get through all of this material. We had the same problem actually in the previous section, so I wouldn't feel too bad about it. I'm a really big fan of tea. And I'm a really big fan of this animation too. It makes me feel calm just looking at it. I have a cabinet filled with tea that I need to make more of every day. You just made tea? Awesome. Tea is nice. Coffee is nice. Whatever you like to drink. I also I have tea. We have some coffee, but we're not big coffee drinkers here. And then I have 2 big things of powdered Gatorade because that's just useful. I want a ramen animation. I would feel too hungry. I don't know if I want to include that. It would just make the entire class feel like they want to eat. What kind of tea do I like? I am a big fan of black tea. I'm a big fan of green tea. I'm pretty I'm not picky, but I do like nicer teas. I feel like I actually can I enjoy the nicer teas as well. So it's not just like normal tea bags. I have the loose leaf stuff and I have pour over. I'm not like the most expert or elite tea drinker, but I do try to follow the instructions and do everything you're supposed to do in order to drink tea and enjoy it. All right, let's go ahead and move on. Let's talk real quick about announcements. I need to go through some announcements we need to cover. Here we go. Where's my mouse? Okay, so there's a survey that just came out last week. I'll make a post about the exact title, but you should have gotten an email about it, just like the last survey we had. This survey is asking you how the course is going and what we can do to improve it, or what I can do to make your life better, essentially, right? So the goal of this survey is to see whether or not you feel like this course is helping you learn, what you can do, or what I can do specifically to help you learn more effectively. And if there's something you absolutely hate, you can definitely let me know. All right. I really do care about making this course as best as it can be, which is why you can be really honest. And I have no way of identifying who you are, right? GSU sends out this survey. They anonymize all of the information, so I can't tell who said what. So I'll just get a list of comments, feedback, right? If you want to say something really mean to me, you definitely could. That would hurt my feelings and make me cry. But if you want to use this form to tell me what about the course you don't like and what I can do to maybe improve the course, that would be really, really helpful, right? So if you haven't found that survey yet, or if you've been putting it off, please, please, please fill it out if you can. It will really help us improve the course. Other things you should know, exam 1 is out, as you all know. If you missed the exam, let me know and I'll find your exam for you. But I think I found everyone's exam and put it into iCollege. By the end of today is the hope that homework 2 grades should be out, right? It might take a little bit longer. One of our TAs is under the weather, so it's taking him a little bit longer. But we're close to shipping out homework 2 grades. And then by the end of the week, quiz 3 and quiz 4 should be out as well. Okay. Corrections for homework 1 were done yesterday, but corrections for homework 2 will be due next week. It is too late. You know what? Yeah, it is too late. It is too late. It would be unfair for me to give an exception for this section and not the other sections, right? So it is too late. We might have a kind of like a chance later on for you to get more correction points, but we set the deadline for Monday. We gave you a week, so we're gonna stick with it, right? We want to not be the type of staff or the type of class that keeps pushing deadlines over and over again. That would be weird. Quiz 6 is this week. So the next lecture, it'll cover what we're covering right now, including and also what we covered last week. So graph properties, DFS, BFS, and topological sort. All right, so let's go ahead and take a look at topological sort. Give me a sort in chat if you're ready to learn. Deep breath here. Someone in the other class asked, what should you type if you aren't ready? I don't know. Tell me something. I don't know. Tell me a secret. Tell me something that you like about yourself. Tell me something good that happened to you this week. I don't know. If you're not ready, I'm at least happy that you're here and that you're trying your best. All right. So a topological sort of a directed acyclic graph G is equal to V comma E. A topological sort on a DAG is a linear ordering of all its vertices such that if G contains an edge U comma V, then U appears before V in the ordering. If the graph contains a cycle, then no linear ordering is possible. Nice. We should be able to take the quiz now, right? Now you understand everything. I'm just kidding. This definition is really hard to understand at first, but I promise it's not that scary. It's exactly from what you saw in the textbook, but here are 3 ways to understand this. It's a fancy way of saying, give me a list of nodes from your DAG. So I want all of my nodes in a certain order. Each node on the blunt end of the arrow will appear before the node on the pointy end of the arrow, right? Just dumbing it down as much as possible. If you have a node and another node and the arrow goes this way, then this node better show up first in the ordering before this node, all right? What is DAG? It's a directed acyclic graph. So no cycles and there's arrows on the edges. Remember, DAG stands for directed acyclic. Oh, the reason why you're confused is because I'm dumb. The reason why you're confused is because we didn't go and look at this one first. So let's take a look at directed acyclic graphs, the definition. Good call out. This is why I appreciate student participation. Okay, so when we have a graph that's directed and has no loops, we call that a directed acyclic graph. These graphs have certain properties and definitions we care about. If we take a step back and think about directed graphs in general, there are two things we care about. There are sources, which are nodes with no inbound edges, and there are sinks, which are nodes without any outbound edges. In fact, I'm going to go ahead and type this on the top right so that we can use this later. So a node with no inward arrows is a source, and a sink is a node with no outward arrows. Okay? So we'll use this very soon. DAGs, on the other hand, are used for representing real-world dependencies. So we'll see that very, very soon, right? So here's an example. We have GSU courses. How do the prereqs map out between these courses? We have 1301, we have 1302, we have 2510. You have to take all these courses in order. So one example is that we take 1301 first, and then we take 1302, and then we can take 2510. From there, we can take 2720, which allows, and also take 3210. And then if we take 2720, then we can take 4520. If we take 3210, we can take 4210, right? This is an example of a directed acyclic graph. There are no cycles. There's no way we would say that you have to take 4520 in order to take 1301. That wouldn't make any sense, right? If you understand and if you feel good about this, then we want to use the definition from the previous slide. This is a directed graph. What are the sources and what are the sinks? I'll give you 10 seconds. All right, what is the source here? Right, it should be 1301. 1301 is the prereq before all other prereqs, right? This is the class that we absolutely have to take. So this is a source. There's no arrows pointing into it. Cool. Now I'll give you another 5 seconds to type up what are the sinks that you discovered here. There should be more than one of them. Which nodes are considered sinks? Go ahead and type it in if you have it. Okay, so this node is a sink and this node is a sink. All right. Everything inside here has an arrow going outward and therefore it can't be a sink. This is very much like, if you know the water cycle from like elementary science, there's, a source, which is where the water comes from, usually like a mountain top with snow that melts and stuff. It goes down the river and then it ends in a lake or an ocean, which is a sink. Right, so the ocean doesn't go and have more rivers coming out of it, right? That is the end all be all. So in this case, 4520 has no other arrows pointing out. 4210 has no arrows pointing out. Okay. So another example that we'll go through real quick. Is this a directed acyclic graph? I'm going to go ahead and say yes, because we already saw this graph from before. There's no cycles here, and there's still arrows pointing, right? I'll give you about 20 seconds. What are the sources and what are the sinks? And then if you're done with that early, go ahead and answer these next 2 questions. All right, which nodes are sources here and which nodes are sinks? Go ahead and punch it in if you have it. So a source here are all of the nodes without any arrows pointing to them, right? So the 2 nodes that have arrows not pointing to them are 2 nodes without any arrows pointing at them. Is this node here, this node 3, and this node 5, right? Sinks, on the other hand, are nodes with not any outward arrows. So that's this one here and this one here. Okay. So sources in this case, sources are 3 and 5 because they don't have any arrows pointing inward. Sinks are 2 and 6. If we ran depth first search starting at 4 and followed only the outbound edges, what would we print out? Now you have to remember how DFS works, but I'll give you about 10 seconds. It should be relatively straightforward. What do you think we'll actually output? What nodes would we actually visit? Okay, punch it in chat if you have it. We'll start with the node we start with, right, which is 4. We're going to call DFS on 4, which means we'll print it out. And then we'll go and visit all of its neighbors. It only has one neighbor in this case. It's 4. So we end at, sorry, it's 2. And we end at 2 because it itself has no neighbors, right? On the other hand, if we wanted to go and call DFS on the node with 3 in it, this will be a lot more involved because we're going to start with 3. We're going to look at all of its neighbors. So in this case, we'll look at this neighbor with 1 in it. So we'll print out, so we'll print 4 and 2 here. And then we'll print out, in this case, we're going to print out 3. And then we're going to print out all of its neighbors. It's 1 first. And then 1 is going to look at its neighbors. It's going to print out 0 afterwards because we look at the smallest labeled node. So between 0 and 2, 0 will go first. And then 0 will look at all of its neighbors, which will be 2. And then 2 doesn't have any neighbors to look at, so we'll be done there. We'll return false from here if we use the pseudocode from homework. And then we'll go back to where 0 was. Well, when we were calling recursively on 0, 0 doesn't actually have any more neighbors, so we go back to where 1 was. 1 will look at 2. Realize that it's been visited before, so we go back to 1 because we realize that we don't need to print anything there. We don't have to make another recursive call. And then once we're done with that, 1 is done, it'll return false. And we'll go ahead and continue the call on DFS of 3, which we'll try to call on 4, right? And it will succeed because we need to not forget that we have to look at all the neighbors of 3, including all the second neighbor, which has 4 in it, right? So in this case, we start with 3, we mark it as visited, we visit 1, we mark that as visited. Every time we visit, we print it out. And then 1 will look at its neighbor, which is 0. 0 will look at its neighbor, which is 2. We'll go back to 0 once we realize 2 didn't have any neighbors. We'll go back to 1 once we realize that 0 is out of neighbors. 1 still has one more neighbor. We follow this edge to 2. We realize 2 is already visited, so we go back to 1. We say we're done here. We return false. We go back to 3 because that's where we were at when we called DFS on 1. And 3 still had a neighbor, so we go ahead and call DFS on 4. We print out 4. We mark it as visited, and then we come back to 3. We run out of elements to process, right? Because 3 has no more neighbors, and then we return from here. Okay? Now that if we felt good about this, we're going to go ahead and take a look at topological sort. Topological sort here is calling, again, finding an ordering of nodes in a graph that is directed and acyclic. So that means that a valid topological sort will have all the prereq nodes appear before all the nodes that depend on those prereqs. Easier if we look at an example, but before we do, a sort here means differently than the sort that we talked about before, right? Before we were ordering numbers from largest to smallest or smallest to largest. Topological sort is kind of a misnomer because we're not actually sorting the same way we did in the earlier part of the class, right? We're taking a graph and we're trying to flatten it into an ordering of nodes. So in this case, what is a valid course schedule to take, assuming that you only can take one CS course per semester? And just to spice things up, let's just say we have its own, like an own edge here, which is Psych 101. This obviously does not have any dependencies on any of the CS courses, but we wanted to take Psych 101 as well. I'll give you all about 30 seconds, or 20 seconds to think about what a valid ordering here is by visiting the dependencies. So the question here is, what is a valid course schedule to take, assuming you can only take one course per semester? And we also want to take Psych 101. Okay, go ahead and punch in chat if you have an example. We know we want to take 1301. We could take Psych 101 when we want, so let's just take Psych 101 next. Then we'll take 1302, and we'll also have to take 2510 before you can take any of the other classes. You could take 2720 after that, and then 4520 after that, and then 3210, and then 4210, right? That's one option. We could also say, let's not take any CS classes our first semester. Let's just take Psych 101. And then we can take 1301. From there, we can take 2510 in first, and then 1302 if we wanted to. Then we could take 3210 and then 2720 if we wanted to, and then 4210 and 4520. Right? There are a couple of different options here, and we don't have time to go through all of them. But the idea here is that every single prerequisite is early in the list compared to the other requisites that it satisfies, right? So we definitely want to print out, or we definitely want to output 2720 only after we've already outputted 1302 and 2510. Okay, so we're going to go ahead and skip to how we would actually code this out. Here, neighbors don't matter in ordering. Yeah, the neighbors don't matter in the ordering. We can do it in any order we want as long as the prereqs are satisfied before we print out the current nodes. So if you think about how we would actually approach this, notice that some valid orderings kind of go through depth first, almost like path by path, until we reach a sink. So that's essentially asking us to use DFS. There's going to be a demo that I'm going to walk through really quickly now, and then in the next lecture, we'll go through it in more detail. All right. So let's go ahead and do that now. We're going to take a look at a graph. We need to look at a directed acyclic graph. So let's go ahead and do that. Here's a graph. And we want to call depth first search on this one, or not depth first search, topological sort, the DFS version, right? And I'll just show you what we're doing. We want to call DFS a bunch of different times on each of the nodes that are not yet visited. And once we go and finish calling DFS on each node, we're going to add that node to the back of some list. And then at the end of all of that, we're going to reverse the list. All right. So it's easier to just show you what I mean. At the beginning, we start with a list that's equal to empty. And then we start by calling DFS on the node with the smallest label, in this case, DFS on the node 0. 0 is going to try to look at all of its neighbors. We mark it as seen, right? Mark it as visited, then look at all of its neighbors starting with the lowest labeled 1. So we look at 1. We look at 1, we mark it as visited. We look at all of its neighbors, which is going to look at 2 next. 2 is marked as visited. Then we go and look at all of its neighbors. In this case, we're going to look at neighbor 3. 3, mark it as visited. Then we look at all of its neighbors. We're going to look at 4. At this point, 4 has no neighbors, right? If this is the case, if 4 has no more neighbors, then we can go ahead and output 4 and put it into the back of the list. So we're going to put 4 here. Now, when we're done there, we're going to go back to 3 because that's where we were when we called DFS on 4. And 3 is out of neighbors as well, which means we have to add this into the list. If we're adding it to the back of the list, we're going to go ahead and add it here, right? And so if we add here, then we end up with we're done here and we move on to the previous node that was called. In this case, we go and look at the 2, because that's where we called DFS on 3 from. And DFS on 2, let me try that again. Once we're done with calling DFS on 3 and we add 3 to our list, we go back to the world that called DFS of 3, which was DFS of 2. DFS on 2 still has one more neighbor. It has 5. So we're going to go ahead and look at 5, mark it as visited, and then add that to the end of our list because it has no neighbors, right? And so at this point, we've looked at all of the neighbors of 2. That means we can process 2 and add it to the list as well. And then from there, we go back to where we called 2 from, which is 1. And 1 is going to try to look at its neighbors. It's going to look at 3. 3's already been visited, so we ignore that. And so we go ahead and mark the 1 into our list as well. From there, we go back to 0. 0 still has neighbors, so we look at 2. 2's been visited, so we go back and we're done with processing all the neighbors of 0, in which case we output
0 here. All right. We're not done yet because we have to look at all these other nodes that we haven't yet visited. The key here is that we're going to look at the smallest labeled node first. So we're actually going to look at the 6 before the 7. So what that means is that we're going to look at 6, process that. 6 gets processed. It has no neighbors that we can visit. Once it's marked as visited, we're done. We add 6 to our node. To our list rather, and then we do the same thing for 7. We visit 7, we try to process its neighbors. 6 has already been visited, so we're done with all of its neighbors. And then since we're done there, we add 7 to our list. All right. I know we went through this really quickly, so we're going to go through it one more time in lecture on next class. And the key here is that we're going to reverse the list and end up with a topological sort. In this case, we're going to say 7, 6, 0, 1, 2, 5, 3, 4, right? And that will be an ordering. We notice that we can visit 7, which will be a prereq of 6. So then we can visit 6 next. And then we can visit 0, which will, that is a prereq for 1 and a prereq for 2. So then we can visit 1 next. Since we satisfied the prereqs 1 and 0, then we can print out the prereq for 2, right? Like 2 gets printed out. Now 2, once that's done, we can have the prereq of 5 be satisfied, as well as the prereq for 3. Once the prereqs for 3 are satisfied, then and we output that, then we have the prereq for 4 satisfied, and 4 gets outputted here, right? So what we're seeing is that the order from left to right allows us to visit all of the nodes that are prereqs for other nodes before those nodes are visited. Could use a stack for this? We could definitely implement DFS using a stack instead, and that would still work. There's a couple of questions here, but I'm going to do the takeaways and then answer the questions afterwards. So let's go ahead and do takeaways now. DFS on graphs works the same way as DFS on trees. We're going path by path, except we keep track of whether or not we visited a node. Graphs have these properties that we care about: undirected and directed, right? We started with undirected. Today we looked at directed, and then cyclic and acyclic. Lastly, directed acyclic graphs allow us to model real-world dependency problems, and you can use a topological sort to find a ordering, a topological sort of the directed acyclic graph, which shows you what sort of dependencies we need to satisfy before we can visit other nodes in the graph, right? That's all I had for today. Thank you so much for sticking with me. If you have any questions or concerns, I'll answer them now. We're in office hours right now, so you can definitely stick around and we'll continue answering questions. Otherwise, have a good night. Thanks for your time, and I will see you in class next lecture.